As mentioned before, there are different principles for the actual generation of the speech signal. They may be rule-based or data-based, they may be parametric or non-parametric, but in practice there are actually 4 principles which have proven to be practically relevant and to produce naturally sounding speech signals. These are the parametric synthesis, the concatenative synthesis, which comes in 2 flavors, also called the unit selection synthesis, and finally a synthesis approach which is based on hidden Markov models, HMMs. The first such approach, the parametric synthesis, is one which you already know from chapter 6 of this course, because it's mainly based on the source filter model of speech production. The idea is to identify all the parameters which are used in the source filter model for producing a particular sound and putting values which correspond to that particular sound. So we first need to differentiate whether this is a periodic sound, then we need to decide about the fundamental frequency, perhaps including a glottis filter, or if it's a noisy sound, then the noise signal to be generated. We can amplify those excitation signals and add them in case we have a mixed excitation, and then transmit everything through the vocal tract filter, which here is modeled as a parallel structure of different formant filters. As you know, these formants are important for the characteristics of the sound to be produced. So for each sound to be produced, we have to put values for all these characteristics of the speech production process. Unfortunately, this source filter model is a rather simplified version of the speech production process, and this is why the speech signals which come out of such a process are relatively limited with respect to their naturalness. In order to deal with that problem, people have thought of recording speech signals from real speakers, from natural speakers, and concatenating them in a way which allows still the manipulation of different prosodic characteristics like the amplitude, the fundamental frequency, and the length of the individual sounds, but still using natural speech which should sound more natural than the one produced with the source filter model. We usually take units which correspond to transitions of different phones, as you see here in this example, and then these units are cut out in a pattern which is equivalent to the pitch, that is the fundamental frequency when the glottis is open, is marked here first, and then a little segment of this signal is cut out corresponding to this pitch period. These individual segments can then be manipulated with respect to their amplitude, for example, in order to produce an intonation, with respect to their fundamental frequency, for example, by putting 2 segments instead of 1, and of course also by with respect to their length, by just using more of those segments. And they are then overlapped and added to form a new speech signal which has different characteristics. For example, here you see that the fundamental frequency, or the period corresponding to the fundamental frequency, is smaller, the fundamental frequency is higher than in the original sample here. We call this process the pitch synchronous overlap and add, or PSOLA algorithm for concatenating speech units. And it's usually based on transitions and on small units like diphones, and it involves a lot of manipulation of the speech signal, which then unfortunately results also in quite some unnaturalness of the resulting speech signal. People have tried to avoid this unnaturalness by putting less manipulation into the speech signals, and this can be achieved by taking longer units, for example words or phrases or sentences. If we concatenate those longer units, we have to find the ones which are fitting best to the speech signal to be produced, but also which fit best amongst themselves, which means that this synthesis approach is based on the calculation of a so-called cost function, which consists of concatenation costs, the cost that the units fit amongst themselves, and the so-called target costs, that is, the cost that the unit which is used for the synthesis actually fits what needs to be synthesized. So the principle of so-called unit selection synthesis is to find an ideal sequence of units which minimizes the costs in terms of concatenation costs and target costs. The quality which can be achieved by this unit selection principle can be relatively high in case that the units which are in the inventory of this synthesizer fit well to the units which need to be used in order to produce the text which is desired. That is, the quality depends quite a lot on which text you would like to synthesize, and it also depends quite a lot on how many and which units you have in your inventory. This makes usually the inventory of such a synthesizer a relatively large one, so this is a synthesis process with a rather large footprint, requiring lots of memory. In case that you do not have such a large memory available, you can make use of the fourth principle, which is based on hidden Markov models. As you know from automatic speech recognition, hidden Markov models can be used to find a path between states, and this path then can be optimized by calculating the probabilities. Something very similar happens if you want to concatenate speech units. You can try to find a path across a parameter space and then select the parameters which optimally fit your synthesis task. This is done in two steps. You first have to train the hidden Markov model in terms of providing a speech database and training parameters related to the excitation process and to the vocal shaping process, which correspond to individual sounds, which are included in the labels here, and then put that information into a trained hidden Markov model. In the second step, during the synthesis, the text is analyzed, the labels are extracted, and then this hidden Markov model helps you to generate an optimum set of parameters, both for the excitation and for the vocal shaping. And then these parameters can be used in a standard parametric speech synthesis process. The results from this hidden Markov model-based synthesis process are rather good, although they might not necessarily reach the quality of a unit selection synthesizer, depending of course on the inventory of that unit selection synthesizer. The big advantage of the hidden Markov model-based approach is that the inventory is much smaller. The footprint of this synthesizer is much smaller than the one of a unit selection synthesis.